Okay, good morning, and my name is Valeriano Villar, and I'm going to solve and discuss the question for number 1 and number 2. So let's watch this. Okay, for number 1, we have the problem. An oil engine takes in air at 1.01 bar and 20 degrees Celsius, and the maximum cycle pressure is 69 bar. The compression ratio is 18 by 1, and calculate the air standard thermal efficiency based on the dual combustion cycle. So let's assume that the heat added at constant volume is equal to the heat added at constant pressure. So let's first write the given. So given we have the compression ratio of 18. We have the temperature for the initial temperature 20. So this is Celsius. So let's add 273 to make it Kelvin. So it makes 293 Kelvin. So we also have P1, the initial pressure, which is 1.01 bar. We also have our the P3 or the P4, which is 69 bar. So for dual combustion cycle, the PV diagram is a constant, which is this one, the diagram. So in solving the thermal efficiency is equals to 1 minus the heat rejected over the heat added. So we need the temperature in all the points. So let's get first the temperature for number 2. So in temperature number 2, at point 2, since this is isentropic process, we have the constant equation for T2 over T1 is equals to V1 over V2 raised to K minus 1. But we all know that V1 over V2 is equals to RK, which is the compression ratio, and that is K minus 1. So solving T2 is equals to, let's get here the T1. We have the T1 293 degrees Kelvin, and the RK, which is 18, and we have the K of 1.4 minus 1. So our temperature in 2 is equal to 931.0577 Kelvin. So we have the temperature 2. So in getting temperature 3, we need P2. So let's get P2. The same process, P2 over P1 is equals to V1 over V2 raised to K from the first cycle raised to K. So this is RK. So P1 RK is equals to K. So our value of P2 is, we have P1 1.01 bar, the RK of 18, and 1.4. So our temperature at 2 is equals to 57.77 bar. Now from process 2 to 3, which is constant volume, we have P3 over P2 is equals to T3 over T2. So our T3 is equals to P3 T2 over P2. Substituting the value, we have T3 is equal to 69 bar times 931.0577 all over 57.77. So our temperature at 3 is 1112.0474 Kelvin. So we have our temperature 3. So getting temperature 4, since it says in the problem that assume that the heat added at constant volume is equals to heat added at constant pressure, we can make an equation of heat added 1 is equals to heat added 2. So for heat added 1, we have mCV T3 minus T2 is equals to mCP T4 minus T3. So from here, we can get the value of T4. Cancel the mass. So substituting the value, we have the value of CV 0.7176 times our T3 1112.0474 minus our T2. Our T2 is 931.0577 is equals to our CP 1.0047. So this is kilojoule per kilogram Kelvin. So we have T4, the unknown, and T3 1112.0474. So from inputting in calculator, we can get the value of T4, which is 1241.4 Kelvin. So we have our T4. Let's get the value of T5. Okay, so at 3 to 4 cycle, we have the constant pressure. Since V3 over T3 is equals to V4 over V4 T4, we can get V4 over V3 is equals to T3 T4 over T3. So we have 1241 for T4 and we have 1112.0474. So the value of V4 over V3 is equals to 1.116. So next, so from the we'll know that from this diagram, our V5 is equals to V1. So we can make an equation of V5 over V4 is equals to V1 over V4. Now we can form an equation of V1 over V2 and V3 over V4. So this is V1 over V2 is RK, and this is the reciprocal of what we get here. So let's put it here. our RK is 18 and the reciprocal 1 over 1.116. So we can get V5 over V4 is equals to 16.4. So we have the value of this. So at process 4-5, which is isentropic, we have the equation T4 over T5, and that is equal to V5 over V4 raised to K minus 1. So this value is this. So let's substitute 16.14 raised to decay of 1.4 minus 1. So we have our T5 is equal to T4 over 16.14 1.4 minus 1. So our T4 is equal to 1241.4. So the value of T5 is equals to 408 Kelvin. So we have already the value of temperature. So now we can get the heat. So we have the heat added total is equals to heat added 1 plus heat added 2. So let's solve. At the heat added 1 we have MCV T3 minus T2 plus MCP T4 minus T2 T3. Okay, so substitute the value since we don't have the mass. Let's set aside this first. So 0.0776 for MCV kilojoule per kilogram Kelvin, and T3 1112.0474 minus 193.0577 plus 1.0047 multiplied to T4 1241.4 minus 1112.0474. So our heat added total is equals to, from calculator, 260 kilojoule per kilogram since we don't have the mass. So let's get the QR. So QR, we have the MCV equation T5 minus T1. We don't have this. So our CV 0.7176, our T5 there 408 minus the T1 293 Kelvin. So we can get QR is equals to 82.6 kilojoule per kilogram. So we can get now the efficiency. Efficiency is equals to 1 minus heat rejected over heat added. So 1 minus heat rejected 82.6 kilojoule per kilogram, and heat added 260 kilojoule per kilogram. So from calculator, cancel the unit, we have the thermal efficiency cycle 0.682. So this is the value. let's multiply in 100 percent, so we can get the efficiency 68.2%. Okay. Okay, so we have the problem for number 2. So the problem is state 1 for a dual combustion engine has a P1 of 180 m and T1 of 60 degrees Celsius, compression ratio of 18. At the end of the constant volume combustion process, the pressure is 7,695 kPa. RC is equals to 1.5 based on 1 kilogram per cycle of a hot air standard and with K of 1.31. Determine the percent clearance, B, the pressure, volume, and temperature at each corner point on the cycle, C, the work net, D, the thermal efficiency, and E, the mean effective pressure. So let's solve for the clearance. Let's write first the given. The given is we have P1, 1 atmospheric pressure, or this is 101.325 kPa. So this is the diagram. So this is the diagram. So let's solve. Let's get T1 is equals to 60.3 degrees Celsius. RC is 1.5. RK 18. P3 is equals to 7,695 kPa. We have the value of K 1.31. So for A, we have the equation. The percent clearance, we have RK is equals to, we have 1 plus C over C. So by manipulating the equation, we can get C is equals to 1 over RK minus 1. So substituting the value, we have 1 over RK 18 minus 1. So from the calculator, we can get 0.0588, and that is equals to and times 100, that is equals to C is equals to 5.88 percent. So let's solve for the B. At point 1, we can get V1 is equals to MRT over P1. So we have 1 kilogram, we have 0.287, and we have 60.3 plus 273 all over the P1, 101.825. So the value of V1 is 0.9443 cubic meter. So this is V1. So for point 2, we know that RK is equals to V1 over V2. So we can solve V1 over RK. We have V1 0.9443 over RK 18. We have V2 is equal to 0.0525 cubic meter. Okay, so we need to get the temperature. So let's solve for T2 over T1. and that is equals to V1 over V2 raised to, this is isentropic process, so K minus 1, so this is RK. Okay, so T1 RK K minus 1, so our T1 is 60.3 plus 273 times 18 raised to 1.4 minus 1. So our T2 is equals to 816.893. Okay, so let's solve for P2. So for P2 we have, for isentropic process, we have the equation P2 over P1 is equals to V1 over V2 is to K. This is RK. So our P2 is equals to, multiply P1, we have P1 1.325 kilopascal, multiply to 18 raised to 1.4. So P2 is equal to 4,468.107 kilopascal. So we already completed the point 2, so we go to point 3. So for point 3, since point 3 is since 2 to 3 is constant volume, V3 is equal to V2, and that is 0.0525 cubic meter. And then from the constant volume process, we have the equation P2 over T2, P3 over T3. We can solve for T3. So our T3 is equals to 7,695. This is T2 and P3. This is P3, and we have T2 806.893, and we have this is P3, and we have P2 4468.107. So the value of T3 is equals to, from calculator, 1406.8579. Okay, so let's go for P3. So let's go for point 4. So for point 4, it is an isobaric process. So P3 is equals to P4, and that is 7,695 kilopascal. So we have the equation RC is equals to V4 over V3. So we can get V4 is equals to RC 1.5 multiplied to V3 0.07875. So we have now V4, and that is equals to 0.0525. So the answer is 0.0785. This is V4. Okay, so let's go for T4. So we have the V3 over T4 and T3 and V4 over T4. So we can get T4 because this is all given. So T4 is equals to, so T4 is equals to V4 T3 over V3, and that is we have V4 0.0785 T3 of 1406.8579 over V3 0.0525, so T4 is equals to 2110.284 Kelvin. So let's go for 0.5, the last point. So in 0.5 we can get some of the 0.5 values from 5 to 1 process, because this is a constant volume. So from constant volume, V1 is equals to V5, and then, okay, so and that is 0.9 is 0. V1 0.9443 cubic meter. So we can get the pressure, because we have P1 over T1 is equals to P5 over T5. So since we don't have T5, let's get T5 from the process 4 to 5 isentropic or constant entropy. So from T5 over T4, that is equals to V4 over V5 is to 1 minus K. So we have already those value 0.0785 and V5, this one 0.9443, and our K, what is our K anyway, 1.31. No, this is 1.31. Okay, clarification. So from this, from calculator, we can get T5 of 976.3 Kelvin. So from this one, we have the value of T5. So P5 is equals to, we have P1 976, P1, have the P1 101.325, and T5 976.3 over T1, which is 60.3 plus 273. So we can get P5 is equals to 296.667 kilo Pascal. So now let's go for C. Work net is equals to QA plus QR. So we have, let's solve for QA. We have the QA is equals to QA1 plus QA2, and that is MCV T3 minus T2 plus MCP T4 minus T3. Okay, so we don't have the value of this CP and CV, so let's get the value. So for CV, we have the equation R over K minus 1. So our R is 0.287 K 1.31 over 1 ay minus 1. So we have 0.9261 kilojoule per kilogram Kelvin. So for CP, equation is KR over K minus 1 and is equals to the K 1.31, the R 0.287 over K1 1.31 minus 1. So we can get the value of 0.2131 kilojoule per kilogram Kelvin. Okay, so I've already the value. Let's solve for QA. So for QA we have 1 kilogram multiplied to CB 0.9261 140.6.8575 6 minus 575 ay minus 8575 plus 1 kilogram CP 0.2131 and we have 211.67 minus 1406 and something. So from calculator we have QA is equals to 1399.696. So for QR we have the equation MCV T1 minus T5. So we have 1 kilogram CV 0.92 61 and 41 we have 333.45 over T5 976.3. So our QR is now equal to negative 595 of 0.343. This is negative because it is rejected. So let's solve for the work net. For the work net, QA plus QR, and that is 1399.696 minus 595.343. So our work net is now equals to 804.353 kilojoule. Okay, so next D for the efficiency, thermal efficiency. So it is work net over heat added. So we have the work net 804.353 over heat added 1399.686, and our thermal efficiency is 0.5747, or that is equals to 57.45%. So last E, for E we have the mean effective pressure, and it is work net over the volume displaced. So, and volume displaced is equals to V1 minus V2. We have already the work net. P mean is equals to the work net 804.353 353, so that is kilojoule. And over have 0.5747. No, we have 0.9443 cubic meter minus 0.0525 cubic meter, and our mean effective pressure is equals to 701.8379 kilo Pascal.